everyone. Welcome to Analysis 1 video 25. This video we're going to be looking at monotonic sequences, increasing and decreasing sequences. So let's start with a definition of what those are, and then we will move on to see what we can do with them. And I am sure that you already have some intuition about increasing and decreasing sequences, but this is quite an important definition because it's sometimes clashes with what we might intuitively think of as increasing and decreasing. So I want to be really clear what the definition is. So let's let AN be a real sequence. We're definitely talking about real sequences here. We say that the sequence AN is monotonic increasing, or monotone increasing, or just increasing, if AN is less than or equal to AN plus 1 for all n. And notice that our sequence, we might have two terms being equal. AN can equal AN plus 1, it still counts as increasing for our purposes. What's the difference between monotonic increasing and monotone increasing? There isn't one. Some people say monotonic, some people say monotone. When I was preparing this section earlier, I came to the conclusion that I really wasn't sure why some people use one word and some people use the other, and I think I might use both depending on what mood I'm in. So apologies if I say monotonic sometimes and monotone other times, but hopefully you'll just know it's the same thing. And to be honest, mostly I'll just say increasing because it's shorter. If we really mean AN is strictly less than AN plus 1, then we need to say strictly increasing. So we say that the sequence AN is strictly increasing if AN is less than AN plus 1 for all n. And then you can guess the next two definitions because they're for decreasing instead of increasing. So we say the sequence AN is monotonic decreasing or monotone decreasing or just decreasing if AN is greater than or equal to AN plus 1 for all n. And we say that the sequence AN is strictly decreasing if AN is greater than AN plus 1 for all n. And then finally, sometimes we want to talk about a sequence that's increasing or decreasing, but we don't care which it is. And we say that the sequence AN is monotonic or monotone if it's increasing or decreasing. Sometimes we will talk about monotone sequences, but it doesn't matter whether they're increasing or decreasing. So let me just remark that a constant sequence is both increasing and decreasing. If you need to, just go back and look at the slide, check the definition to confirm that. I know that that might seem counterintuitive. There are lots of ways that we might define this. It just turns out that it's really helpful to include constant sequences and sequences that are constant for a bit and then keep strictly increasing or whatever. It turns out to be helpful to include those as increasing. And then if we mean strictly increasing, we've got the word strictly increasing to capture that idea. So just be aware that increasing might not completely match your intuition. So what can we say about these sequences? Well, let me draw one of my usual pictures. So non-negative horizontal axis, my vertical axis can be positive or negative. And I'm going to have an increasing sequence here. So maybe it starts being negative and then it goes up a bit, not so much. Maybe it stays the same for a bit. It keeps going up. It does whatever it does. Suppose I know that this sequence has an upper bound. So I'm going to draw an upper bound with a horizontal line in blue. Maybe this is an upper bound. What does this mean? Well, my sequence is increasing, but it can't go above this blue line. So I'm going to have to kind of keep squeezing these terms in somehow. And if you think about it a bit, I think it becomes quite natural to make the conjecture that an increasing sequence that's bounded above must converge. And that's going to be our next result. This is called the monotone sequences theorem. I think that you should think of this as one of the really key results of this course. It says, let the sequence AN be a real sequence if the sequence AN is increasing and bounded above, then the sequence AN converges. And if the sequence AN is decreasing and bounded below, then the sequence AN converges. So the sort of slogan version of the monotone sequences theorem, the version that I remember in my head, says a bounded monotone sequence converges. Just a small detail here. So I've carefully said that if the sequence is increasing and bounded above, then it converges. I didn't say whether it has to be bounded below. But if you think about it for a moment, you'll realise that an increasing sequence has to be bounded below. Think about that. So it doesn't matter whether or not I mention the bounded below, that follows automatically. So a bounded monotone sequence converges. That's the slogan for the monotone sequences theorem. I can't overestimate how useful this is. We're going to see some examples of using this result in this video. You'll see some more on problem sheets. It's really, really helpful. There are a surprising number of bounded monotone sequences in the world, and we know that they converge. Another comment is that this applies to tails of sequences as well. So if the real sequence AN has a tail that's monotone and bounded, then it converges. And we know that the tail converging means the whole sequence converges. So maybe our sequence oscillates in some complicated, not monotone way for a bit. It doesn't matter. As long as from some point on, it's bounded and monotone, that's all that affects convergence. We know that the first finitely many terms of a sequence don't affect convergence, and that can sometimes be helpful as well. Let's have a go at proving this. Let's focus on part one, where we're going to assume that the real sequence AN is increasing and bounded above. And we want to show that it converges. What is the idea here? Let me draw an unofficial picture. Maybe I'll draw an unofficial picture over to the left. So my usual axes, unofficially, and then my sequence has some terms, and it's increasing, and I remember that increasing can mean stays the same, or it might just increase a little bit. But we know that it's bounded above. So let me draw in an upper bound with this horizontal line in light blue here. This is an upper bound. It's not the case that the sequence has to tend to the upper bound, because I might have been very inefficient with where I put my upper bound. If I know that the terms of my sequence are all less than or equal to 1, then 10 is still an upper bound, and the sequence definitely doesn't tend to 10. So I have to be a little bit careful. So what might it tend to? Well, it might tend to the least upper bound. That seems like a more plausible conjecture, sort of homing in on this supremum. If it has a supremum, we'll come to that in a minute. So the idea, I will write unofficially here, is that the set AN, where n is greater than or equal to 1, so the set of terms of the sequence has a supremum. This is just informal. We'll prove this carefully in a minute. And tends to, maybe I should say the sequence AN tends to this supremum. So that's what we're going to try to prove. And I hope that the picture, your intuition, that makes sense of that as a strategy. Let's do this carefully. So let's let S be the set of all AN such that n is greater than or equal to 1. It's good to give the set a name because then we can talk about it. Well, what do we know? We know that S is non-empty because it contains term of the sequence. And we know that it's bounded above because that's what it meant for our sequence to be bounded above. And we know that a set that's non-empty and bounded above has a supremum by completeness. So, by completeness, I realise it's been a while since we mentioned completeness, so you can always go back and look if you want to remind yourself of that, but it says that a non-empty set of real numbers that's bounded above has a supremum, at least upper bound. So by completeness, it has a supremum. And now we want to show that this supremum is the limit, that the sequence converges to this. So how are we going to do this? Well, I drew on an upper bound on this unofficial picture earlier on, but let's say this upper bound was at sup S, the supremum. We want to show that by going far enough down the sequence, we can guarantee that we are within epsilon of sup S for some fixed epsilon. Let's fix an epsilon now. Take epsilon greater than 0. There we go. Why is this? Well, we know because it's the supremum that if we think about sup S minus epsilon, I haven't really got very much space to write this, sup S minus epsilon, if I try to draw this in, I'm going to do a dashed red line. We know by the approximation property that there's a term of the sequence between sup s minus epsilon and sup s. So if I draw in a purple vertical line here, let's say capital N, A capital N, well, maybe I haven't quite got my line in the right place, but A capital N is going to be between sup s minus epsilon and sup s. And after that, from the increasing property, in fact, all of the terms of the sequence are going to lie in this strip between sup s minus epsilon and sup s. And so will be within epsilon of the supremum. So that's my attempt with a picture and my coloured pens to try to give you the intuition of what's going on here. Now let's write it down carefully. So by the approximation property, again, you can remind yourself of that if you don't quite have it at the front of your mind at the moment. There exists an n such that sup s minus epsilon is strictly less than A capital N is less than or equal to sup s. So we know that there's one term that's within epsilon of sup s, but because of the increasing property, actually they all are. So now if n is greater than or equal to capital N, then sup s minus epsilon is less than A capital N by what we just had, and that's less than or equal to A little n because of our increasing sequence, and that's going to be less than or equal to the sup of s by the definition of the supremum. So I'll just draw to highlight that the A capital N is less than or equal to AN. This is because the sequence AN is increasing. Just try to kind of highlight where we've used that. And from this string of inequalities, we see that A little n minus sup s is then less than epsilon. And so the sequence AN converges and AN tends to sup s as n tends to infinity. And that proves that an increasing sequence that's bounded above converges. We still need to do part 2, which is that a decreasing sequence bounded below converges. But actually, if the real sequence AN is decreasing and bounded below, then the sequence minus AN is increasing and bounded above. So actually, part 2 follows from part 1. So we don't need to go through the argument again. It's just an immediate consequence of part 1. So the monotone sequences theorem is really helpful. It's actually not too bad to prove. I think this is a really nice proof. I like the fact that I can draw a picture of it. Just before we start having a look at applications of the monotone sequences theorem, let me mention lemma 39, which says that if we've got a real sequence AN that's increasing and not bounded above, then it tends to infinity as n tends to infinity. So we've just talked about sequences that are increasing and bounded above, and they converge. A real sequence that's increasing and not bounded above tends to infinity as n tends to infinity. And I think I'm not going to write this one out by hand because it's such a short proof. So if we take m in the reals, this is the threshold our evil opponent sets us that we want to jump over. Since the sequence AN isn't bounded above, we know there's a capital N so that AN is bigger than capital M. Otherwise capital N would be a bound. But then because the sequence AN is increasing, if n is greater than or equal to capital N, then A little n is greater than or equal to A capital N is greater than m. So from capital N onwards, in fact, all of the terms are over that threshold. And since we can do that for any arbitrary threshold, that proves the lemma. Let's have a look at some examples of what we can do with the monotone sequences theorem. So one example, I'm going to let AN be 1 plus 1 over n all to the n. And this is a sequence that you've already studied on a problem sheet. On sheet 1, you showed that the sequence is increasing and that it's bounded above. You showed that it was bounded above by 3 on that sheet. And so by the monotone sequences theorem, we know that it converges. Isn't that great? We can show that it converges without having to know what the limit is. A lot of our strategies so far, especially if you want to use the definition, you kind of have to have a guess of what the limit is. With the monotone sequences theorem, we can sort of creep up on a sequence and show that it's convergent without needing to know so much about it that we know what the limit is. So the sequence here, AN converges. If we say it tends to the limit L as n tends to infinity, what can we say about L? Well, we know that an is greater than or equal to 2 because a1 is 2 and it's increasing, and we know that it's bounded above by 3 because you proved that on the problem sheet, and we know that limits preserve weak inequalities. So we know that the limit is between 2 and 3. 2 is less than or equal to L is less than or equal to 3. Actually, secretly, you might know some more about L, but that's entirely unofficial, and I couldn't possibly mention it on a video at this point. Now I'd like to work through another example, and this one's going to be a bit longer and a bit more substantial. So what I'm going to do is let C be a non-negative real number, and the goal of this example is to show that the square root of C exists. So you might remember we showed that the square root of 2 exists earlier on using supremum. We're going to do something much more general here to argue that the square root of C exists, the square root of any non-negative real number exists, using monotone sequences. How am I going to do that? Well, I'm going to define a sequence. I'm going to define a sequence AN by A1 is 1. This might be a slightly mysterious definition for now. And AN plus 1 are going to be defined to be a half of AN plus C over AN for n greater than or equal to 1. So this is a recursive definition. Each term is defined using the previous one, except that we fix A1 as 1. You might wonder, could we be dividing by 0 here? I'm wondering that too. But actually, you can do a quick induction to check that these are never going to be 0. So by induction, can show that AN is not 0 for all n greater than or equal to 1. So this is a legitimate definition. Why are we using this? Well, just kind of go with the flow. Let's just work through it and you'll see how the argument works out. And then you can think about, well, how could you have constructed that in the first place? But I think at the moment I just want to focus on the style of argument because the techniques that we're going to see here are really useful. You're going to find yourself wanting to use them potentially on problem sheets, for example. Hint, hint. And I'm going to claim that the sequence AN converges. We're going to have to prove that carefully. And also, if AN tends to the limit capital L, then L squared is C. Basically, the plan is to show that the sequence converges to root C, and that will show that root C exists in some sense. So it will certainly turn out to be positive. And then we're going to do this in a few steps. So I'll try to make it really clear which step we're doing at any given time. So the first thing, you might want to just go and doodle, fix a value of C, go and experiment with what does this sequence look like, develop some intuition about it. The plan is to use the monotone sequences theorem, so we better show that it's monotone and we better show it's bounded, and we have to decide, are we going for bounded above or bounded below, are we going for increasing or decreasing? And because I've already done my pre-doodling, I'm going to try to show that it's bounded below and then that it's decreasing. So let's show that it's bounded below first. And when I'm doing an argument like this with multiple stages, I like to use kind of bullet points to try to structure. So bullet point sequence AN bounded below colon means that's what I'm about to show. And why is this? Well, actually, you could just check that this is positive, that AN is positive for all n. So we have that AN is positive for all n by induction. I'm not going to write out the details of that. You can probably see how that goes, and if not, you can have a think about it. The next thing I'm going to do, which is maybe not so obvious, is to study AN squared minus C. And the reason for doing that is that it will be useful to us later on. So if I just move my paper up a little bit here. So what can we say? Well, for n greater than or equal to 1, we can use our recurrence relation, so either an plus 1 squared minus c is a quarter of an plus c over an all squared minus c. And if I just multiply out, that's a quarter of an squared plus 2c plus c squared over an squared minus c. And if I bring the c in and do a little bit of rearranging the algebra here, we can see that this is a quarter of an squared minus 2c plus c squared over an squared. But that's a quarter of an minus c over an all squared. And we know that squares of real numbers are greater than or equal to 0. They're non-negative. This is one of my favourite facts. We even proved it back weeks ago at the start of this course. So this says that an plus 1 squared minus c is always greater than or equal to 0. So an plus 1 squared is greater than or equal to c for all n greater than or equal to 1. So from a2 onwards, the square is always greater than or equal to c. And that's kind of relevant because we think the sequence is decreasing and bounded below. Well, we hope that it's tending to the square root of c secretly that we're about to show exists. So this is reassuring in terms of we thought this is what we should have. And actually this gives us a lower bound for the sequence as well. But I think the fact that with more or less one line we can argue it's positive, that's enough for the bounded below. This is going to be useful to us in a moment. Let's move on to the next stage. So my next bullet point, I'm going to try to show that this is decreasing, at least for n greater than or equal to 2. There is a kind of wrinkle about what happens between a1 and a2, but I don't care because that's finitely many terms. So for n greater than or equal to 2, we have, so roughly speaking, I have two strategies here. I could think about the difference, an plus 1 minus an, or I could think about the ratio an plus 1 divided by an, and try to think about whether these things are greater than or equal to 0 or greater than or equal to 1, depending. How do I decide which to do? Well, I just look at how the sequence is defined. Sometimes it's really natural to divide because the sequence is defined multiplicatively. Here, I think it's more natural to think about the difference. So let's think about an plus 1 minus an. So by our definition, we know that that's a half of an plus c over an minus an. And if we rearrange, I think that's going to be a half of c over an minus an, just bringing that into the brackets, which I could write as 1 over 2an times c minus an squared. Suddenly it's quite useful to know that an squared is greater than or equal to c, because that means that c minus an squared is less than or equal to 0. We argued that an was positive earlier. That was relevant at this point as well. So we see that this lot is less than or equal to 0. And so an plus 1 is less than or equal to an for n greater than or equal to 2. And so the tail of this sequence is decreasing. So our sequence is bounded below and decreasing. So by the monotone sequences theorem, which I could write out in words, but I'm going to abbreviate to MST just now, an converges. And that was the first part of our claim. We wanted to show that the sequence converges. We also want to say something about the limit. So let's say an tends to L as n tends to infinity. Please watch very carefully because it's very tempting to write down illegal things at this point, and I'm going to concentrate very hard on doing this nicely, and then you can copy the kind of strategy that I'm using here when you're doing your own ones. Well, one thing we know is that if an tends to L, then an plus 1 also tends to L. That's just a tail of the sequence. If we know that an tends to L, then an plus 1 tends to L. But we also know that an plus 1, because of how we defined it, is a half of an plus c over an. And by the algebra of limits, that tends to a half of L plus c over L. At least in the case when L is non-zero. So let's say an tends to L and L is not 0, and we'll talk about L is 0 in a moment. So by the algebra of limits, an plus 1 tends to a half of L plus c over L. We know that the sequence an plus 1 has a unique limit, so we can equate these. So by uniqueness of limits, we have that L is equal to a half of L plus c over L. And if you rearrange that, I think that's going to give us that L squared is c. So what I want to stress here is how careful I've been to use results that we've already seen to argue about this L, I have not taken a limit of part of this but not the other part, or there are all sorts of mysterious things that people do at this point, but hopefully this is really clear that we are using algebra of limits, we're using tails, and we're using uniqueness of limits. And we also know that an is greater than 0 for all n, and limits preserve weak inequalities. I really like this example because it draws together so many strands that we've already seen about convergence of sequences. So we know that L is greater than or equal to 0. And so L is the square root of C, which kind of exists, if you like. This is a non-negative real number whose square is C. In fact, it must be positive in this case because we assumed that L is not 0, so that we didn't divide by it. What would happen in the case when L is 0? Well, because we know that an plus 1 squared is greater than or equal to C, by the algebra of limits, an plus 1 squared tends to L squared, and by preservation of weak inequalities, L squared is greater than or equal to C. So if L is 0, then C must be 0, and so we still have the result that L squared is equal to C. So I'll just note here that we can handle L equals 0 separately, and I won't go into that because that's not such an interesting case. We've got one more result in this video. This is lemma 40, and I promised this earlier on, so we better do it. This says that log n over n tends to 0 as n tends to infinity. And the plan is to prove this using the monotone sequences theorem. So how are we going to do this? Let's let an be log n over n, for n greater than or equal to 1. And then certainly this is bounded below because it's non-negative. So the sequence an is bounded below. And I claim that it's also decreasing by properties of log, at least a tail of it. So by properties of log, and basically we do some calculus here to argue that this is decreasing. And I can't really see an advantage in working through details of calculus on video now when officially we don't know what calculus is yet. So let's just call this properties of log, and we see that something silly maybe happens when n is 1 and 2 and stuff. I reckon for n at least 100, it's decreasing. A tail of it is decreasing. I bet we don't need 100 here. Probably we can use like 3 or something, but I don't really care. It doesn't make any difference for argument. We need to know a tail of it is decreasing, because then, by the monotone sequences theorem, an converges, which is good news. That's the first thing we'd like to know, that it converges. We also want to show that it tends to 0. Well, let's say that an tends to L as n tends to 0. Sorry, as n tends to infinity. And then certainly by preservation of weak inequalities, we know that all the terms of the sequence are non-negative. And so we know that L is non-negative. And we want to cook up some kind of recurrence relation, a little bit like the way in the previous example we could argue that an plus 1, we could find 2 ways to study the limit of that. But we don't really know anything nice about an plus 1 in this case. But because we know about properties of logarithm, I think it's quite natural to try a2n instead, because we can do nice things. Because a2n, that's log of 2n over 2n, and that's log 2 plus log n over 2n. And by the algebra of limits, log 2 over 2n is going to tend to 0, and log n over 2n is going to tend to L over 2. So that's by the algebra of limits. But also, a2n is a subsequence of an, and we know that subsequences of a convergent sequence converge to the same limit. So a2n tends to L as n tends to infinity. And so, by uniqueness of limits, we're going to have that these limits must be the same. So L is L over 2, and so L is 0. And that's what we wanted. So this strategy of monotone sequences and potentially thinking about some kind of recurrence relation or subsequence or something is really nice. I hope you enjoyed that. This is the end of this block of work. So hopefully you are now all set to tackle sheet 4, and I hope that you find the questions on sheet 4 interesting. In the next block of work, we're going to think more about sequences and subsequences because there's lots to explore. So one thing we might think about is sequences having convergent subsequences. Is it the case that every sequence has a convergent subsequence? You think about it for a minute and you realise the answer is no, because if you think about the sequence 1, 2, 3, 4, 5, 6 forever, that does not have a convergent subsequence. So it's not the case that every sequence has a convergent subsequence. But is it the case that every bounded sequence has a convergent subsequence? That's something that I'd encourage you to have a think about before you watch the next video. Bye for now.